Today we're going to be exploring the concept of constructible numbers. We have three items: a straightedge, a protractor, and a blank unlabeled writing surface. We can draw two arbitrary points on this surface and we can connect them using our straightedge. We'll label this length 1. We note that now that we've defined a length of 1, we can use our protractor to measure this length, and then we can extend the line using our straightedge, place the pivot of the protractor at the end, and draw circles of radius 1 indefinitely at each new intersection. We're therefore able to construct any integer using only these three items. Now suppose that we have two constructible numbers, alpha and beta. We will draw lines of length alpha and length beta at some arbitrary angle with each other. Using our protractor and setting its length to a unit, we will center the protractor at our intersection point, draw a circle of radius unit, and mark that intersection. We'll construct a line from the end of alpha to this intersection using our straightedge. Now, we'll set our protractor to some arbitrary length that's smaller than any of these edges, and we'll draw a semicircle centered at this new intersection. We'll do the same at the end of beta. We notice that we can measure the distance between this intersection and this intersection. So, by setting our protractor to that distance and centering it at this point, we can find a corresponding intersection here, and we can draw a line from the end of beta through that intersection that will be parallel to this line here. Then, by extending the line of length alpha, we've constructed two similar triangles. We'll denote the new bottom length x. Remember that this here is length unit. So now we see that because these triangles are similar, we have the ratio alpha divided by 1 being equal to x divided by beta. So by cross multiplying, we see that alpha beta equals x. That is, that for any two numbers, alpha and beta, that we've already constructed, we're capable of constructing their product, x, which is this length here. We'll now examine a similar construction. We have two numbers, alpha and beta, that are both constructible. We'll construct a line of length alpha, and we'll extend that line to be of length beta. Right now we're assuming that beta is larger than alpha, but we'll touch on the other case when we're finished. Now, at some arbitrary angle, we'll construct a line of unit length. We'll draw the line between the end of alpha and the end of the line of unit length. And using the construction shown previously, we'll draw a line parallel to this, starting at the end of beta. We'll extend this line until it intersects this line. Again, we've constructed similar triangles. We'll call this length x. Now, we note that alpha over 1 equals beta over x. So cross multiplying, we have alpha x equals beta, or x equals beta over alpha for alpha. we note that we can divide in either way as well. This construction does not imply that we can only divide larger numbers by smaller numbers. Had beta been smaller than x, it would simply end here. We construct a line here. We call this distance x. And the resulting math would be the same. Now let's consider a construction where we begin with a point and we extend it a unit in one direction and some constructible number alpha in another direction. We'll set our protractor to some length that's larger than half of this total distance, and we'll draw circles of that radius about both ends. We'll use this to construct the midpoint by drawing a line through the intersections of those two circles. We'll now place the pivot of our protractor on this midpoint, measure the distance to the end, and draw a circle of that radius, a semicircle. Now, we'll draw a line upward from, I'm going to erase this just to make it a little bit easier to see. We're going to use the same methodology by choosing an arbitrary radius, setting our protractor to that radius, marking points at both sides, choosing a slightly larger radius, drawing circles of that slightly larger radius, and then drawing a line through those points to construct a line perpendicular to this line that goes through our initial point. And we'll draw that line up until it touches our circle. Now, with our straight edge, we'll draw lines from this intersection to the end of alpha to the end of 1. We know from Thales' theorem that this triangle is going to be right. That is, this angle is a right angle. We also note that these two triangles are going to be similar. This is fairly easy to see because we know that this is right, and we know that these two angles must add up to 90, but also that these two angles must add up to 90. So whatever we add to this to get 90 must be this angle and this angle. So these must be the same, these must be the same, and we have two similar triangles. What that means is that if we call this side x, then we note that we have x over 1 equals alpha over x. By cross-multiplying, we get x squared equals alpha, or x equals the square root of alpha. We therefore see that we're capable of constructing the square root of any constructible number. So far, we've shown that we can construct integers, rational numbers, and the square roots of rational numbers. Now I will briefly show that we can also add and subtract these numbers. So suppose we have a rational or a constructible number, alpha, and we have another constructible number, beta. We can set our protractor to length beta, place our protractor at the end of alpha, draw an arc of radius beta from this point, and then extend our line until it reaches that arc. Now, of course, this new distance is alpha plus beta. Similarly, if we set our protractor to length beta and draw that arc in the other direction, then we see that this length here is alpha minus beta. Therefore, we've shown that our constructible numbers are closed under multiplication and addition, that they have additive inverses, and because we've shown that we can divide them, that they have multiplicative inverses. This shows that the constructible numbers are a field. We note that since we're capable of constructing perpendicular lines, as shown before, we can start at some arbitrary point, move a constructible distance in some direction, and then perpendicular to that, move another constructible distance in that perpendicular direction. We're therefore capable of constructing any points with constructible coordinates alpha, beta. Now, let's consider the ways that we can construct new points. We recall that the only things we're capable of constructing are lines using our straightedge and circles or circular arcs using our protractor. Let's first consider the situation of trying to construct new points using the intersection of two lines. We must begin with two constructible points, which we'll call x1, y1, and x2, y2. We can then use our straightedge to construct a line through those points. Now the equation of this line is going to be y minus y1, we're going to use point slope form, equals our m is going to be y2 minus y1 over x2 minus x1, x minus x1. Now, since we know that our constructible numbers are closed under subtraction and division, then our entire slope is already a constructible number. So I'm just going to write that as m. So we have y minus y1 equals mx minus mx1. Again, we've shown that our numbers are closed under multiplication. So mx1 is also constructible. I'll call that a. I can subtract, I can add y1 to both sides. We'll say a plus y1. We'll call that b, and okay, we'll call that b tilde, and then we'll say b is negative b tilde, so we can get our standard form. And we now know that we can write a line in standard form with m and b, our slope and y-intercept, all being constructible numbers. Now consider we have two lines here. Let's erase this for a second. And those lines have equations y equals m1x plus b1 and y equals m2x plus b2. Now subtracting these two equations, we get 0 equals m1 minus m2x plus b1 minus b2. Again, we're closed under subtraction. This is constructible. This is constructible. I'm going to subtract this to the other side. So we're going to get b2 minus b1 over here equals m1 minus m2x. If x equals, we're going to divide these. And so now we have a constructible number divided by a constructible number, and we've already shown that's constructible. So using the intersection of two lines with constructible coordinates doesn't yield any new constructible numbers that we haven't already shown to be constructible. Next, we'll consider the situation where we have the intersection of a line and a circle. The line, of course, must be constructed by 2 points that have constructible coordinates. We've shown before that such a line is form mx plus b, y equals mx plus b, where m and b are constructible numbers. The circle must have a constructible center and a constructible radius. We'll call the center of the circle x1, y1, and we'll label the radius r. Then, the equation for our circle is x minus x1 squared plus y minus y1 squared equals r squared. Then the equation for our line, as we stated before, is y equals mx plus b. Now, we notice that we have an equation here for y that we can plug in for our y here. So instead of y minus y1 squared, we can say mx plus b minus y1 squared equals r squared. Now, we notice that when we expand this, we're going to get x squared terms here. We're going to get x squared terms, some x terms, some constants, and similar over here. We notice we're not going to get any terms higher than x squared. And of course, since we've already discussed these constructible numbers are closed under addition, subtraction, multiplication, and division, all of our coefficients are going to be constructible. So ultimately, we're going to be left with an equation of the form ax squared plus bx plus c equals 0. And we're going to just assume that I've already subtracted this r squared, which we know is also constructible, over into this side. And that's why we have 0 over here. Well, now we know that we can solve this using the quadratic equation. And so our x, and that's going to be the x position of the coordinate of the intersection of our circle and our line, negative b plus or minus square root b squared minus 4ac all over 2a. And once again, b squared, 4ac are all constructible numbers because, again, they're closed under all those operations. This is going to be closed over division. So we're going to be left with a number that we've already shown can be constructed. So once again, an intersection of a line with a circle does not produce numbers that we have not already shown to be constructible. Now let's consider the situation where we're finding the intersection of two circles. We'll call the center of this one x1, y1, the center of this one x2, y2. This radius will be called r1, and this radius will be called r2. Then, our two equations are x minus x1 squared plus y minus y1 squared equals r1 squared, and x minus x2 squared plus y minus y2 squared equals r2 squared. We notice that when we expand both of these equations, the coefficients of x squared and y squared are both going to be 1, which means that after some algebraic manipulation and consolidating all of the x terms and constants, we'll be left with two equations of the following forms. X squared plus y squared plus, and we also notice that we're never multiplying x and y together. So we'll have ax plus by plus c equals 0. And I'm just going to actually a1, b1, c1. And then for the second one, x squared plus y squared plus a2x plus b2y plus c2 equals 0. Now, when we subtract these two equations, these square terms are going to cancel, and we're going to get a1 minus a2x plus b2 or b1 minus b2y plus c1 minus c2 equals 0. Now, this can be easily rearranged into a typical equation of a line, right? We can isolate y just using typical algebra, and that means that we have an equation of a line and an equation of a circle that we can then use to find x and plug that back in to find our y. And we just showed previously that the intersection of a line and a circle results in numbers that we've already shown to be constructible. So once again, we've shown that the intersection points of two circles with constructible centers and radii are already shown to be constructible. Recall that we began by showing that we can construct the rational numbers. Then we showed that we can construct the square root of any number, meaning that we could take the square root of any rational number. Since we also showed that the constructible numbers are closed under addition, subtraction, multiplication, and division, it means that we're able to construct the entire field of the rational numbers adjoined to the square root of that alpha. We note that these are the only two ways that we can construct numbers, as we've proven that the intersection of lines, a line and a circle, and two circles does not yield any additional numbers. We also note that if we begin with the field of rationals, we can adjoin some alpha to it, we can adjoin the square root of some alpha to it to get a new field that we'll call F2. We can adjoin the square root of another constructible number to it to get F2. And here we're considering the square roots of numbers that aren't already in our previous field, right? We're not talking about the square root of 4. We're talking about numbers that aren't perfect squares and that we haven't already adjoined the square root of or adjoined the square root of a factor of. And we can do this indefinitely because there are indefinitely many primes. Now, what this also means, though, is that if we have any beta that is in our set of constructible numbers, there must be some point along this chain where we find the minimal f sub k that it's contained in. Now, since we're adjoining a square root, which is the root of a quadratic, then the degree of the extension f sub I over f sub I minus 1 is going to be equal to 2. And so, consequently, we know that since we have degree 2, degree 2, degree 2, it means that if we've reached, the kth group, or the kth field in the chain, then we have the degree of f sub k over q is equal to 2 to the k. Now consider the problem where we have a cube of length 1, of side length 1. Now, of course, we know that this cube has volume 1. Now, of course, by definition, the side length 1 is constructible. And so a question we could ask ourselves is, can we construct a cube, can we construct the side length of a cube whose volume is 2? In other words, can we construct x such that x cubed equals 2? Well, of course, such x is a root of the polynomial x cubed minus 2 equals 0. And we note that this polynomial is irreducible. What this means is that its root, the cube root of 2, which exists in this field extension, has the degree over Q of 3, since this is the minimum polynomial. But we've shown that the minimum field in our chain that any element that is constructible exists in is 2 to the power of k. And since 3 is not 2 to the power of any integer k, then this field does not exist anywhere in our chain, which means that the cube root of 2 is not constructible. Therefore, it is not possible to double the cube. Another fascinating problem to consider is, suppose we construct a circle of radius 1. Is it possible to construct a square such that the area of this circle equals the area of this square? Well, we note that the area of this circle is pi r squared. R squared is 1 squared, which is 1. So here our area is pi. Well, if we have an edge length of this circle L, in order for the areas to be equal, then we have L squared equals pi, or L equals the square root of pi. Now we know that pi is a transcendental number, which means that the square root of pi is also transcendental. Since all of the fields in our chain of constructible numbers are constructed using square roots, then all of these fields are algebraic extensions, which means that a transcendental number, and also its square root, which must also be transcendental, will never occur, which means that constructing a side length of the square root of pi is impossible. Now I'm going to prove a simple lemma, namely that the cosine of an angle and the angle itself are constructible from each other. First, suppose we've constructed some angle. Then, as shown previously, we're capable of constructing a line perpendicular to our bottom line here, straight up. Now, the cosine of the angle is this length divided by this length. And since we've shown that we can construct the quotient of two numbers, we can easily construct cosine of theta by alpha over beta. Similarly, suppose we just know that alpha is the cosine of some angle. We can construct a line perpendicular to alpha, to the line of length alpha, upward. Then we'll set our protractor to length 1 and draw an arc so that it intersects this line. We'll then connect using our straight edge that intersection to the start of alpha, and we've constructed our angle theta. Once again, what we've shown is that constructing an angle theta and constructing cosine of theta are interchangeable. Another question that we might ask is whether it's possible to trisect an angle. That is, given some angle called 3 theta, is it possible to construct theta? Now, using the lemma we just proved, this is equivalent to asking, given 3 theta, given cosine of 3 theta, can we construct cosine of theta? Now, we recall the identity that cosine of alpha plus beta equals cosine of alpha, cosine of beta, minus sine alpha, sine beta. So, cosine of 3 theta equals cosine of 2 theta plus beta equals cosine of 2 theta, cosine of theta, minus sine of 2 theta, sine theta. Now, using some identities that we know that cosine of 2 theta is equal to 2 cosine squared of theta minus 1. So here we have 2 cosine squared of theta minus 1 cosine theta. Sine of 2 theta is 2 sine theta cosine theta. So now in this term, we notice that we have 2 sines, 1 cosine. So I'm just going to write that as 2 sine squared theta cosine theta. And then we can use our Pythagorean identity. We know that sine squared of theta is 1 minus cosine squared of theta. So 1 minus cosine squared of theta cosine theta. I'm going to just rename cosine as alpha just to make this algebra a little bit easier to look at. So we have 2 alpha squared minus 1 alpha minus 2, 1 minus alpha squared. There's another alpha at the end. I'm just going to put it here so I don't get confused. Okay, so then we have 2 alpha cubed minus alpha minus 2 alpha plus 2 alpha cubed. So in total, we have 4 alpha cubed minus 3 alpha. Okay, so now suppose we're trying to trisect the angle 60 degrees to construct an angle of 20 degrees. In that case, our 3 alpha is 60, so our cosine of 3 alpha is a half. So this is equal to cosine of 3 alpha, which is a half, which means that the alpha is the root of the polynomial 4 alpha cubed minus 3 alpha minus a half, which is irreducible over the rationals, which means that the extension field for the root of this polynomial has degree 3, which once again is not a power of 2, which means that the root of this, namely cosine of theta, is not constructible. And so consequently, using the lemma I just proved, the trisection of an angle is unconstructable.